So we'll get a similar situation here. So the low frequencies and the high frequencies will look like the overdamped case on the previous slide. What will be different is in between the low frequencies and the high frequencies. And so in general, we'll get a Bode diagram that looks something like this. So this is the magnitude plot, this is the phase plot, and this is plotted where this point here is omega n. And so what you can see is just what we sort of predicted. At low frequencies, our magnitude plot is flat. At high frequencies, our magnitude plot has a slope of minus 40 dBs per decade, where each pole contributes minus 20 dBs per decade. And with the phase, at low frequencies, we have a phase of 0 degrees, and at high frequencies, we have a phase approaching minus 180 degrees, where each pole contributes minus 90 degrees of phase. In between, the behavior is a little different between the underdamped and the overdamped. In particular, when zeta is small, when we don't have a lot of damping, we get this sort of resonant peak here, where we get some amplification in the neighborhood of the natural frequency. You can see this sort of trend where decreasing zeta results in more resonance with more amplification. And similarly, you can see what the effect is on the phase, where the S gets steeper. So the intermediate sort of slope gets steeper with less damping. In this class, it's not necessary to exactly draw the Bode diagram of a complex conjugate pole perfectly. We just want to know basic trends. What's the behavior at low frequencies? What's the behavior at high frequencies? And what is the effect of zeta on the in-between? Just trends in terms of increasing resonance or decreasing resonance. Furthermore, when we have complex conjugate zeros, we have a very similar shape. It's just reflected over the horizontal axis. So this is the same sort of trend we saw with simple poles and simple zeros and differentiators and integrators. But instead of starting off at 0 and going down at a slope of minus 40 dBs per decade, a complex zero will start off at 0 and go up at plus 40 dBs per decade. And the phase, instead of going down to minus 180, will start at 0 and will go up to plus 180. So this brings us to the conclusion of Module 20. In this module, we introduce how to draw Bode plots, where we recall that Bode plots display frequency response information in two graphs, one graph being magnitude versus frequency and the other graph being phase versus frequency. We then learn two approaches for drawing the Bode diagram. One is a point-by-point approach, a brute force approach, which we in general will not employ. You calculate the magnitude of the complex number when you substitute s equals j omega into the transfer function and then convert it to decibels. And then you calculate the phase or the angle of that complex number when s equals j omega is substituted into the transfer function. And we also learned a straight line approach. And the idea is that we take a given transfer function and split it into components, simple gains, simple poles, simple zeros, integrators, differentiators, and complex poles and complex zeros. We then memorize a library of Bode diagrams for these simple components, and we draw the Bode diagram for each piece of the larger transfer function. Then we add the graphs together using the mathematical properties we introduced earlier in this module.